Alrighty, in this video we're going to talk about handling our slopes. So there's really just two of these methods that we need to take care of. They're already being invoked in the appropriate place. So that means that just by implementing these two methods, our slopes should work properly. So let's look at some code, or let's look at some cases where things might not work the way we expect it to. Let me take this platform and duplicate it, this dirt full, and then I'm going to rotate it, and then I'm going to make it really big, like that. And then I'm going to move it down, and then I'm going to move it like that. So this should give us a nice little playground for working with some of the code. I also want to take my main camera and move him so he can see that bit right there. Okay. So as you see right here, we kind of handle slopes, sort of, but things get a little broken, especially around the corners and around coming up the slope. And you see that, yeah, things are just pretty much not exactly what we want them to be. If we take a look at the box collider, it looks like the box collider is a little off on the edge, so that's probably why we're seeing that. But we want to handle these cases a little better. So let's go ahead and work on that. So handle vertical slopes. What we're going to do is first, we're going to get the center of where we're casting our raycast. So I'm going to say var raycast bottom left dot x plus raycast bottom right dot x divided by 2. And what's that going to do? Well, it's going to, like I said, it's going to give us the center of where we're casting our vertical rays. Then I'm going to say var direction equals down, which of course is vector 2 up negated. Then I'm going to say var slope distance equals slope limit tangent times raycast bottom right dot x minus center. Then we want to get our slope ray. So our slope ray vector is going to be a vector 2 that starts at the center and goes to the raycast bottom left x. Right? Okay, so let's go ahead and draw that ray. So let's go ahead and say debug draw ray, and then we'll pass in a start of slope ray vector. We'll pass in a direction of direction type direction times slope distance, and we'll pass in color white. Or how about color yellow? So what we're going to see here is so as you see right here, this is only invoked if our delta movement y is smaller than 0, meaning we're going down and we are grounded. Because that method's going to be invoked all the time, we'll be able to see our debug ray happen. As you can see up here, if we go into our scene view, you'll see that this player is indeed casting that ray. And that ray, if he's grounded. It looks like we have some problems with our positioning, so we might want to take a look at that. Coming back into our code, let's go ahead and read through this. Raycast bottom left plus raycast bottom right x divided by 2, which will give us the center of where we cast our rays. Direction is down. Slope distance is the slope limit tangent multiplied by the raycast bottom right minus center. And then our slope ray vector is going to be our center and our raycast bottom left x. No. Why would I pass in a x value into a y vector, y component of a vector? Yes, the problem was right there is I was see, this is why it's good to debug your stuff, and especially do the debug draw ray stuff. Make sure that your assumptions are correct. In this case, I'd accidentally substituted an x for a y, so make sure to change that back to a y. Coming back to Unity, we should see a nice example of what we should see, which is that ray that only gets casted when we're on the floor, and it's going to be used to detect a slope. It's going to be used to detect a slope by casting that ray and getting the angle between itself and the normal of the ray that was hit, or of the raycast point, raycast hit. So let's go ahead and do that. Let's do raycast hit equals physics 2D dot raycast, passing in slope ray vector, direction, slope distance, and platform mass, since we only want to collide with platforms. Then I'll say if not, raycast hit return. So if we didn't hit a ray with our magical slope ray vector, then we just leave and exit the method. All right, now we determine if we're moving down a slope. So is moving down slope is equal to math.f sine. Now, this is actual math.f.sine as in SIGN, not math.f.sine SIN. So we want math.f.sine. What the sine method returns is it'll return a 1 if the number is positive, a -1 if the method is negative, or if the value is negative, or a 0 if the value is 0. So we're going to do sine equals raycast hit dot normal dot x equals mathf dot sine delta movement x, and then if we're not moving down a slope, then return. This will throw an error, or not throw an error, throw a resharper warning because we're comparing two floats with each other with the equality symbol. In this case, resharper wants us to replace this with a comparison using an epsilon. However, because I know the values of sine will return 1 or -1 or 0, I'm going to alt-enter on this and suppress this warning with a comment. Whoops. Come on. No, I don't want to do that. There we go. Okay, so I want to suppress that warning with a comment. Okay, so the next thing we want to do is we want to make sure that if we're going up, that the angle is a valid angle, or rather that the that there is some sort of angle that we're... I'm doing really bad at saying words right now. What we want to do is we want to get the normal of the raycast hit and get the angle between that and the up vector and make sure that it's not equal to 0. Because if the angle between the up vector and the raycast hit normal is 0, that means we're standing on something that we're perpendicular to, which isn't what we want. In that case, we're not moving down a vertical slope, or we're not moving down a slope. So in that case, what we're going to do is we're going to just early exit out. So I'm going to say if math.abs, or actually I want to store this in an angle. I want to say var angle equals vector2 dot angle of raycast hit dot normal and vector2 up. If math.abs angle is smaller than 0.001f, then return. Why? Well, that means that we're not actually on a slope. We're on something that's perpendicular to us, and if we're on something that's perpendicular to us, then it's not a slope by definition, and we don't want to handle anything. Okay, so finally we got all this stuff handled. We're sure we're on a slope. We're sure we're moving down. So let's go ahead and do some stuff. I'm going to set state.isMovingDownSlope to equal true, and then state.slopeAngle equals angle. Then I'm going to say delta movement.y equals raycast hit point y minus slope ray y. So it's kind of the same thing as what we're doing with our other move vertically, is we're ensuring that we can't get any further down from this. But we do want to make sure that we're marking ourselves as moving down a slope, and we do want to know the slope angle, for whatever reason that you might have to store that information. Alrighty, now that we've written our handle vertical slope, let's go ahead and write our handle horizontal slope. I'm going to go ahead and full screen so we can get some more screen space in here. The handle horizontal slope method is going to start off by saying if mathf dot round to integer angle equals 90, then return false. So obviously we don't want to be able to move up an angle that's 90. So we don't want to handle that. Next up, if the angle is greater than parameters.slope_limit, then the delta movement x is 0. That means if we're trying to move up a slope that is too steep for us, then we just early exit out, set our horizontal movement to 0, and return false. Or sorry, and return true, specifying that we have overridden the delta movement x value. Next up, if delta movement.y is greater than 0.07, so if we're moving up-ish, then return true. Otherwise, delta movement.x plus equals. If we're going right, we want to add skin width. Otherwise, or we want to subtract skin width. Otherwise, we want to add skin width. And then we set delta movement.y to equal to mathf_abs, mathf_tan, angle, and then of course we want to convert it back into radians, which is going to be mathf.rad to degrees, or sorry, degrees to rad, multiplied by delta movement x. Now we know that we're moving up a slope and we know that we're colliding below. So we can simply say state.isMoving upslope is true, and state.isColliding below is true, and then return true. So this code effectively replaces the other logic that we had in our move horizontally, but with slightly different results. In this case, we modify the movement of our vertical movement. We modify it based off the angle of the slope that we're moving up. Okay, so now that we've written that method, let's go ahead and see what happens differently. We should get a much smoother experience here. And we do, actually. We get a very nice experience going down, but our going up, we can't go up. Why can't we go up? Because our this angle is too steep for our parameters. So let's go ahead and make this angle a little less steep so that we can go up it properly. So now we can go down and we can go up. And the speed in which we go up is affected by the angle of the thing that we're moving against. Alrighty, so we now have slopes implemented. We now have jumping implemented. We have horizontal movement and we have vertical movement. And you see we get some nice movement up the slope and nice movement down the slope. Of course, we could come in here and say things like click on our player and set our slope limit to like 90 degrees and then make this like that. If we were to do something dumb like that, then you'll notice we can still move up it, which obviously isn't what we want. But just pointing out that you can change the slope limit parameter in order to change how much of a slope the player can move up or down for. Alrighty, sound good? I think that pretty much wraps up slopes, gravity, horizontal, and vertical movement. All right. The next thing is our platforms. We want to handle our moving platforms. Notice how when we jump on these guys, weird things happen. Like we get stuck in them because they're moving too, and see we just got stuck in it again, and we don't quite, we can't quite stay on them. That's because we don't have any code in our character controller that handles an object that we're standing on moving. So what we want to do in the next video is handle any arbitrary object that might be moving under our feet. We want it to take us along for the ride, so to speak, and add its velocity to our velocity. So we'll do that next video, and see you guys then.